Okay, so this is our statistic project with Ruthie, Ariel, Maribel, and Angie. So we decided to do a project on does stretching for 2 minutes before doing jumping jacks improve the total number one can do in 30 seconds. So the methods that you will see within our project is the response variable, which in the response variable is the total number of jumping jacks. It is also measured by how many you can do in 30 seconds. Our control group is one of the factors left controlled is the amount of time you are performing the jumping jacks, which is 30 seconds, and stretching for 2 minutes before performing the task. Our uncontrolled group could be how tired you are going into the experiment or how hydrated you are and or any physical and medical situations. Our explanatory is stretching for 2 minutes versus not stretching. And our confounding is if you were dehydrated or lacked some sleep, you would probably perform worse than someone who was hydrated and had good sleep.
Ruthie Rosema talking about Statistics Project. This is the footage and evidence we have for the people that performed for our question that we had at hand. I would recommend just watching on your own time or else this will take a very long time. But there it is. So for the statistics and data that we got from the video and from our volunteers, we see that volunteer 1 with no stretching performed 33 jumping jacks compared to after 2 minutes of stretching of giving time of rest, they performed 35 jumping jacks. And in the video you'll see a clip of volunteer 1 doing his jumping jacks, and then it just cuts to the next clip of him doing the jumping jacks after stretching for 2 minutes. So you'll see the volunteers doing it before and after, just like with a quick cut. Volunteer 2 for no stretching performed 36, and after 2 minutes of stretching, 43. Volunteer 3 was no stretching of 34, and after 2 minutes of stretching, 45. Volunteer 4 is no stretching 37, after 2 minutes of stretching, 41. Volunteer 5 is no stretching for 34, and after 2 minutes of stretching is 39. Volunteer 6, no stretching at 32, and after 2 minutes of stretching, 36. As you can see, there is definitely an increase of how many jumping jacks each person is able to perform after the 2 minutes of stretching. And also like to point out volunteer 5 and 6, they are both females and they both performed less overall, which just kind of says something about biology and how we are all created differently. For our 5 number summary, you can see before stretching for quartile 1, or as known as the min, we got 32, and then after it was 35. And then for the quartile 1 is 33.25, and then after stretching it was 36.75. Quartile 2 is 34, and then after stretching is 40. Quartile 3 is 35.5, and then after stretching 42.5. And then our quartile 4, also known as the max, we got 37 before stretching and then 45 after stretching. So again, you can see the definite increase in numbers from the after stretching compared to the before. And then for some of our graphs here that you can see, you can just see the numerical data here down below, like the numbers on the graph on the left here for the jumping jacks before stretches. It ranges from around a 32 to a 38-ish, as you can see, compared to the jumping jacks after stretching. It's more around a 35 to the 46. So you can see the numbers on the right graph are a lot higher compared to the numbers on the left, which just show the increase of performance they were able to perform after the 2 minutes of stretching.
This is Ariel talking about or presenting the empirical rule and calculations we did for our data in the empirical rule. So this right here, it was the table that we used for all our calculations for the first, second, and third standard deviation range and the lower row and the higher row, as well as our tables where we recorded our theoretical yields and actual yields amongst all of them. And so In our first question, does the actual distribution of the data correspond with the theoretical distribution suggested by the empirical rule? The distributions do not match with the theoretical distributions because, as we can see, the theoretical yield for them both ended up being 4.8, 5.7, and 5.982. And our actual yields that ended up matching for both was 5, 6, and 6, which affected our percentages to not match up with the typical 68%, 95%, and 99.7% in the empirical rule. And our second question, is it appropriate to apply the empirical rule to your data? It does not seem appropriate to apply the empirical rule to our data as far as we got, because 83% of the data is within the first standard deviation range, and leaving the other two ranges to be both 100%, and like all data is in both of those ranges, and which contributes to the histograms not following the bell-shaped and symmetric distribution of the usual empirical rule of the 68, 95, and 99 percentages. As seen in those charts, they're all pretty even except for before stretching we had two data points that scored the same, but for the rest they all varied and only got one each. And the final question, compare ranges obtained from the empirical rule to see if the experimental group shows a shift in values compared to the control group. There does not seem to be a shift in values between the two groups because, as shown in here, they both match exactly the same, seeing as the control group is both 566 or 83% and 100%, and same with the stretching. So there is no shift in values between the ranges of each group.
So for conclusion, we came up with, where does the mean response for the experimental group fall in the distribution of the control group? And what does that imply about the experimental group results being the same or different as the control group? And our other ones were, how many control group standard deviations is the mean of the experimental group away from the control group mean? What does this imply? What does the statistics and empirical rule say about your question? How strong is the evidence one way or the other? What are some possible extensions you could do to the experiment?